Okay. Hello, everybody. My name is Ryan O'Hara. I'm the Technical Director of Aerospace and Defense at nTopology. And today I wanted to talk to you about how we can use nTop platform to actually do laser powder bed fusion build quantification. And specifically, we're going to focus on a few things. We're going to leverage some of the advanced manufacturing capabilities in our software, and we're going to allow that to ultimately compute or use to estimate the build time and build cost of a component. It's going to be a high-level overview of a fairly detailed workflow. If you have further questions, I'd be happy to either follow up today during the webinar itself or in person or via web video link after coordination with our product and sales team. So with that said, let's get started. One of the things I want to show you here, I have an assembly that I've just brought in from into our software. And in this case, it's of the MIT Cheetah. It's a four-legged quadrupod used for research purposes and is based off of work by many well-known industry folks, specifically in Boston. So along those lines, I thought this would be a great part to show how I've developed a workflow in an nTop platform. We have the ability to accept inputs, and then we have this body section where we do operations. And then finally, we have an output section in the lower left here. And so what I wanted to do is just going to show how this object works. And the idea is that I set up some properties for laser powder bed fusion. So if you're not familiar with that, it's an additive manufacturing process where we use a laser to hit metal. And in a previous life, I actually ran and stood up a metal additive manufacturing lab and was very familiar with material processing. And so what I wanted to do is take that knowledge that I had in this lab and then transfer that for application for our designers, right, in this scenario. And I'm sure at many companies, for those that might be participating, you have an additive manufacturing group, and they would use this similar knowledge base to and could share this with you as a designer, right? And so what I want to do here is I'm basically just going to click on a part. Maybe it's this part. And one of the things when we're building things, we may not know the ideal position or orientation of an object for printing or fabrication. And what we're going to do is in this examples, we're actually going to show how that can be used. So in this case, I've selected this object. I'm going to create a variable of this part and drag this up here. And then what I'm going to do is I have a section here called CAD body input. And what I'm going to do is I'm going to take this object and I'm going to drag it in here. And then you'll see that I have some processes kind of running in the background. And what is actually happening is that this part is being oriented and then sliced. And then we're running computations on that to determine the best orientation of that part. And down here in our lower left input here, you can see our processing toolbar, and you can see how things are going. So we have this part that we started with, and what we're going to do is go through this workflow, and ultimately we're going to use a design of experiments where I'm going to actually position this part in 27 different orientations, and I'm going to run the slicing and the build process analysis to compute how long it'll take to build that part. So if we go here to the position object, and so underneath the hood, I'm actually meshing this object, and you can see I've created these 27 different objects with different orientations. Actually, the correct orientation would be XY, which is like this. And I've positioned these parts so I can more easily visualize them. And then what we're doing is we're actually performing laser powder bed fusion contour and hatching. So we're actually generating the slicing of this object and computing the exact path of the laser. We're including coder time as well. So if our coder time is computed in this section here, right? We're going to look at our contour time, hatch time, and then ultimately we're computing a total time. And when we're designing, it's very important that a design we consider cost when we're designing that part, because if we know a part's really expensive and certain operations are going to be difficult, we might actually want to remove those upfront in the design process to cover cost. And so in this case, we allow the user, in this case, to select from a part from an assembly. And then ultimately, we're going to find out that we're going to pick a part with the best orientation, right? And that orientation is going to minimize a few things. Mainly in terms of additive manufacturing, it's going to minimize supports, right? And if we want to look at the supports, we can see here that this algorithm and then the orientation of 27 different parts, identified, in this case, one of two scenarios that produce a part with the lowest cost. And in this scenario, it appears to be this guy right here. Now, this technique has identified this, and the important part of nTopology is that this process is repeatable. So I can actually go back up. I'm actually going to isolate our original Gina, and maybe I want to do analysis on another component, maybe this motor housing right here, or motor leg piece right there. So we can just do that. We can actually drag this chip right in, and then we're going to rerun those calculations. And the cool part here is that this repeatable process, right, is leveraging that knowledge that I had previously, and we're going to ultimately come up with the cost of an object. And in this scenario, this is a little slightly more complex part, and it's running through the algorithm. I'll complete here shortly. But this is taking those 27 parts, creating meshes from them, slicing them, and then running these calculation costs. And one of the biggest things that you'll see is there's actually quite a bit of variation in the total time. In this case, the time varies anywhere from 4 hours, maybe 1.5, 5 hours. So anywhere from 1.5 to 6 hours, right? So quite a big difference in terms of build prep and orientation, and identifying that up front is very important. Okay, so let's see. In terms of, so that's the total cost. So in terms of cost, right, those cost has a big, is mainly determined because of the time, right? And in this case, the way I've set up this algorithm is that it's going to look at an input cost associated with machine time, right? And so in this case, I put a cost of $150 per hour, and that's how we're computing the cost here. Okay, so, and that cost is just a multiplication, right, of a material cost times the distance traveled, or in this case, the material cost. So that's a property associated with volume, which is another calculation we also include as well. Okay, so with that said, let's look at this new setup here. So we're going to isolate this object. In this case, it's going to be our support volume, and we will get our objects. Right, our 27 different objects. So in this case, you can see we're trying to minimize build volume, and then let's identify the winner here. So we can easily view that. And the winner is this guy over here. And as you would expect, anytime we can minimize the support volume, right, and we're going to minimize the scan time associated with that part. One thing I have not done yet, though, is we're purely computing the volumes. And in our software, we also have the ability to generate supports. I'm not going to show how we do that here today, but we could actually include a cost per number of support for removal. So if it costs per se maybe $1 for one support removal, we could factor that into our cost algorithm here, and that could be applied. So there's a number of uses that could be this could be used for. Okay. Overall, this is a pretty quick scenario of how we can use build volumes. I'm going to go and check in to see if we have any questions. Let's see here. Let's see. Okay. As far as I can tell, we don't have any questions. I think the key here is to emphasize is that nTop, with our implicit modeling technology here, in this case, we're actually focusing on mainly on our ability to process CAD geometry, right? And then to generate meshes from those geometry, ultimately slice those meshes, and then use our build preparation capability to compute support volume requirements based off of overhang angle. That's one thing I'll scroll back up here and we include the ability to vary overhang angle. In this case, I can make it min overhang angle or etc. And let's just put in 45. And we should see some of our requirements change quite a bit for this here. And you can see the number of supports required by changing this overhang angle dropped quite considerably, right? And we can also set some feature size. Maybe I want to refine this volume, so I'll actually change this 1 millimeter. This might take slightly longer to compute, but overall we can use the variable inputs of our nTop platform or of a nTop file, and we can compute quite a bit of information from those. Okay. We'll just let this complete here. But you can see the power of how we're able to do this orientations. Maybe one other thing to include is we have this concept of list processing. And this is the ability where I'm actually able to take a rotation vector and provide those inputs. And so with list processing, this almost acts like a for loop. It allows us to do operations over and over, but not actually having to do any physical programming to do that. Overall, I hope you all found this very helpful. And if you have any questions, please feel free to follow up with I or our sales team. And look forward to talking with you in the future. Take care.